Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Sam Moulton from the Business Review, and I will be your host. It's our pleasure to have Olympus with us today, who will be discussing an introduction to time-of-flight diffraction, TOFD, and its role within the non-destructive testing field. Today's guest speaker is Nicholas Bublitz, Global Product Support Specialist with Olympus. I'd like to welcome you to our webinar platform On24. You'll notice that the webinar is browser-based, so if you disconnect at any point, just click on the link you received via email to rejoin. In order to ask questions, you can send these in via the Q&A widget, which is at the bottom of your screen, or you can type them into the questions box at the top left-hand corner and then press submit. We'll try and allocate around 10 or 15 minutes at the end of today's session in order to address any of your questions or thoughts. You click on the red survey widget, you'll find a few questions in there for you to answer in order to provide feedback. You can do this during or immediately after the webinar. Click on the green resources, you'll find some links in there from our speaker to view. On the yellow help widget, if you require assistance at any point, you can also move and resize and maximize any of these widgets in front of you to get a better view. But now, without further ado, please allow me to welcome Nicholas.
Good morning, good afternoon, good night, depending on where you are in the world. I want to extend a welcome and thank you both to Business Review for hosting as well as all the attendees. Looks like we have a great turnout. We have a little bit of a challenge today, very broad topic, pretty diverse audience depending on how much ultrasonic knowledge you have. But we'll try to, as Sam said, allow a little time at the end to answer some questions. Anything goes unanswered, we'll definitely address it one way or another. So without further ado, we'll go ahead and get started. You can see on the agenda here, pretty chronological order. Go over a little bit of theory and basics on time-of-flight diffraction, some important advantages and limitations, go over the main types of TOFD mainly used in the industries, a few different applications, look at instrument and software equipment considerations, look at some of the new and emerging stuff that kind of where the direction TOFD is going, and then briefly on code standards, recommended practice, and the required typical training and certification that goes along with time of flight. And then, as we said, just a little bit of time for the Q&A session. So without further ado, we'll go ahead and start this race. So really, time of flight started back in the 70s. Most sources push it to the UK, usually as a research tool before it came into the NDT industry. For a while, it was kind of big in Europe, and it kind of got a bad name in a few other parts of the world. As we'll see as we go, it can be quite simplistic to set up, but the analysis and the proper use takes some care and practice. So for a short period of time, it was not very popular outside of Europe. Today, it's much more popular in the Americas and globally, and we'll look at a little bit why, but it's a very powerful NDT inspection tool, so it's kind of had a resurgence in the last 5 years. Used globally at a high volume, mainly because it has some very unique characteristics and benefits from other NDT techniques as well as even other ultrasonic techniques. Today, part of that insurgence of more and more use of TOFD is the modern portable equipment advances that have come along with the advancement in PC chips. Allows us to have very powerful instrumentation at a lower cost. So TOFD, along with phased array and some of the advanced ultrasonic, are really coming into a full bloom. Also, industry trends, a lot more emphasis on safety, growth of fitness for purpose programs, radiography replacement. Many more companies are trying to get away with the safety requirements, the regulation requirements, the cost associated with the radiography technique, and ultrasonic is one of those volumetric techniques that can easily replace that, and there's a lot of codes and ways to go about that. We'll look at that a little bit. And then just in general, the increase in the use and code acceptance of advanced ultrasonics, kind of following on the footsteps of phased array. Phased array is having a huge advent in the codes. So we're seeing not just the use of TOFD in Europe and Asia, which has been pretty typical throughout the years, but we're seeing a real surge globally. So just a little bit on the basic theory. It's a topic we can't spend too much time on just because it can be a little complicated depending on your ultrasonic knowledge. But the main difference between other ultrasonic techniques is the diffraction method. We look at most flaw detection, corrosion techniques when we're dealing with ultrasound. Most of them are reflection techniques when we apply them in the field, meaning we send out, it reflects back at the same angle, and then we monitor that signal and make a call. TOFD is actually a diffraction method where we hit the flaw, we flood the area with a whole bunch of sound, and then the idea is that the space, the volume, whether it's a lack of fusion, whether it's a crack, something of a different density like a slag inclusion, we basically, at the particle level, that whole flaw will vibrate and send out a diffracted energy in all directions. So we're not really worried about the angle that hits it. Basically, we want to pick up all the different areas of diffracted energy from the flaw, and then we're going to use some techniques to measure and analyze that indication. Normally use a pair of probes. If we're doing weld inspection, that's one on each side. There are instances we'll see later where we might do a variation of that, but typically we have one probe that's sending the sound, the other is set up to the receiver on the instrument, and that's really the sound that we're getting back and the sound we're interested in. So the main difference that we really see with time of flight is, unlike pulse echo, phased array, shear wave, we're not really all that concerned about the amplitude response of the signals. As long as we can hit that with enough energy, make the flaw vibrate, and get a little bit of sound back, we're going to use the time of flight to make our length, height, and other indications to whether or not that flaw is okay to remain inside whatever we're inspecting. TOFD is most commonly used on carbon steel for a variety of reasons. There is application to other materials, but due to the grain homogeneous of carbon steel, it makes it much more easier to apply TOFD, and we'll see that as we go through the presentation, some of the reasons why. It's used on a wide variety of applications, from plate to pipe to pressure vessel and a whole host of other components. So just before we get too heavy in the theory, one thing about TOFD is it's very easily set up and applied. The difficult parts really become in the in-depth theory as well as the proper analysis. So a lot of the theory is going to look a lot complicated, but in practicality, just a basic understanding of it and adherence to some basic parameters and rules. You don't have to be a certain expert at the theory. But it's going to look complicated for a while, but it's not as simple, so don't get overwhelmed. So really, TOFD is able to be applied basically by manipulating a concept of beam spread. So when we think about ultrasound and we draw it on chalkboards in training classrooms, we often think of ultrasound as a straight line. Well, in reality, we all know that it's not a straight line. We have a variety of frequencies, a variety of spread of that energy. Anytime we're dealing with ultrasonic or any other type of energy, really. So we really are allowed to use TOFD as a useful tool because we manipulate the concept of beam spread in two different ways. First of all, when we basically pulse the instrument, the sound goes through the wedge. We have beam spread that occurs inside that wedge. And then once that sound goes through the coupling material into the actual material we're testing, we get another effect of beam spread. So we actually get a good manipulation of beam spread, which allows us to use a very small transducer and get a very wide volume of coverage that is very useful and one of the main benefits of time-of-flight diffraction. So we actually also have different wave modes. So we can see here, if we use a TOFD, we're using longitudinal waves. For a variety of reasons we'll see, but that in the wedge we have a longitudinal wave. In the material we enter longitudinal waves with the center being at whatever angle the wedge is cut at. But in reality we have a whole big spread of longitudinal waves, as we can see in blue, and we also have usually shear waves occurring which we can see in the red at about half that angle across the spread. So it's important that we are understanding of this. We set up the proper display. We're aware of what mode we may be looking at. So this is one typical part different from traditional ultrasonics, where we're normally using one wave mode and kind of ignoring the other, although it can show up every once in a while. So just a little bit deeper look at the wave modes. So typically when ultrasonics, there's a whole host of different wave modes that occur, but typically when we're actually doing tests for flaw detection or thickness, corrosion, we're typically dealing with two main types, longitudinal and shear wave, and it's really just how they move through the material. Down to the particle and grain levels, you know, if we send longitudinal wave in, oscillates as shown on the top, kind of sending it in a forward energy pattern, and shear wave is known to propagate in a side-to-side fashion. So when we're dealing with TOFD, we have to be aware that we have both of these wave modes present. So we can see kind of the diagram on the bottom, kind of again showing a lot of things can happen. We send out a longitudinal wave with time of flight diffraction. It starts as a longitudinal wave, but when it hits a flaw, we also have mode conversion there. So almost every incident where we use sound, every time we have an occurrence of that sound striking something, usually different wave modes are generated. So when we set up the display, which we'll see in the next few things, we just always want to be aware of which zones we're using, where the signal might occur, and what may be the propagation mode. And it makes it pretty easy because these two wave modes travel at distinct different velocities. So the reason we use longitudinal waves as the main detection and sizing area for time of flight diffraction typically is because they are about twice as fast. So we know when they're going to occur, and they're going to occur first. Just want to be aware not to use the mode converted areas too much. So here's our first real look at a typical TOFD display. We have what we call the lateral wave, and we'll go into these a little bit deeper. Travels just under the surface. It's not truly a surface wave, and this is important for a few different factors we'll look at. It's going to arrive first because it's basically almost a straight line from probe to probe. We have a region of what would be our inspected volume, which is typically longitudinal waves. We have what we call a back wall. So if this was a plate or a weld, this would be the reflection and diffracted energy coming from the actual backside of the component or the ID of a pipe. And then we have a large area of what we call the mode converted area. This is going to be a mix of those signals. So these could be longitudinal and shear waves that traveled all the way as their longitudinal shear waves, or it could be a longitudinal wave that struck a flaw, converted to a shear wave. So this is the kind of area that we want to be very cognizant about and pay a little bit of attention to. But the reality is, when we're actually doing the testing, it's this one zone, which simplifies it a lot, which we want to stay within that longitudinal realm to simplify everything. We often leave this mode converted area on just because it can offer some unique advantages. It allows us to see more spatial resolution in some cases near the top and the bottom. So it's kind of a fail-safe area. We're simply going to do all of our detection and sizing within this area. So a little bit deeper look at the main signals. So again, the lateral wave is a very near surface wave that travels directly across. It is not a surface wave or a creeping wave. If you're familiar with those terminology, if we had a cap on the top of this weld, it would not actually follow the contour of the cap or any other geometry in our part. It needs a certain amount of volume of material to actually exist and propagate. So it's like almost a near 90 in most setups, going across and then going through the coupling medium, being able to be transmitted into the receive probe. So again, this is going to arrive first. It's usually designated as 0 or for depth purposes, or the top surface of a pipe or weld that we're inspecting. It's really important to understand that it's not a real surface wave. You can't be blocked out by damping with your finger. It's very important for curved components, especially as we can see in the picture a little bit. might be a little bit hard to see, but if we have a curvature to our component, and actually the more obtuse that gets, we're going to have a small area of uninspected area on top of the fact that it's not a true surface wave. There's always a minimalistic, at minimum, dead zone associated with TOFD, and we'll look at that and how to adjust it a little bit. The other one is the backwall signal, which is also typically majority longitudinal wave. It's a typically very wide signal, which can cause some resolution issues at the back, another area that we call a near blind or an area of concern. Not as much as the lateral wave, because we can actually make some focusing and other adjustments to make this very small indeed, but there will always be some very small zone at a minimum that is an area of concern that we want to be cognizant of at the back wall. This is typically a very wide signal because the back wall of a pipe or the back wall of a plate gives a lot of surface area for both reflected and diffracted energy to occur. So we're getting a lot of energy coming off that, and it's very consistent. It's a very big target. And then we have typically another big reflection from the shear wave that we showed coming out at about half incidence. Mainly reflection. We can see it in the bottom picture as well. It's the third main line across. Another large one. And then in between that, we have what we call, again, that kind of mix zone or that mode converted area, which may be a healthy mix of stuff that went all the way as shear, part way as longitudinal, part way as shear. Again, good for added resolution of flaws. We might get a better separation between the back wall and the flaw itself, or the lateral wave and the flaw itself, because of the change in travel speeds. So we often leave this on as a fail-safe. You can see in the picture here, we can actually see different instances of the same flaw in the different zones. So in our longitudinal area, as well as our mode converted area. And the spacing between the signals allows us to have that as a fail-safe area. So a little bit about the wave modes. So typically with most flaw detection, as well as many thickness measurements, a lot of times we use what's called a full wave or a half wave, positive or negative. There's just different ways of displaying the energy that we're receiving back. So if we took a normal weld inspection with a pulse echo shear wave probe, for example, we're taking a sum of all the energy and basically just showing the positive component typically. So we're taking all the positive and negative components of that energy and displaying them in one positive way. And the reason for this is we just want to make sure that we can detect small flaws. We're worried about amplitude. It's usually the way to display it. And a lot of thickness and a lot of delamination, composite type applications, we might actually look at the actual positive and negative separately. And that's in fact what we do with time of flight diffraction typically. We actually look at the RF or unrectified RF signal because we want to be able to look at the peaks of both the positive and the negative energy. The reason for this is it allows us to use TOFD as a very accurate measurement tool. We want to be able to see the shift in a signal from positive to negative because this indicates basically an acoustic impedance mismatch. So example, when we have a steel to air interface, the basic signal would flip from positive to negative. Example would be a lack of fusion is basically a big pocket of air along the bevel of a weld. So we want to be able to identify these unique characteristics in positive and negative. It's going to allow us to identify basically the tips of certain flaws so that we can very accurately measure them using time. So we can see on the display here, if we normally set up a time of flight diffraction setup and we're just looking at the lateral wave and the back wall, we're going to go from the baseline, and the peak of the lateral wave is either going to be positive or negative depending on whose instrument you're using and how it's wired. But the back wall is always going to be 180 degrees or the exact opposite, in this case negative from that positive peak. because of that steel or whatever the material is to the air which is surrounding it interface that we have at the back wall interface. So these tips are really what we're looking for when we're going to do precise sizing, is really the foundation of how we use time to measure with time of flight diffraction. Just a different example here. So these tips become very important. We want to be able to measure them very accurately, and it's going to give us that precision sizing capability. So a little bit on the grayscale display. So we start with an unrectified RF signal, and then we further manipulate the fact that we can see both a positive and negative component in order to set up very useful displays to be able to investigate large volumes in a rapid rate. So we take those components, if we scan something, we look at every signal, and based on our encoder or our data collection setup, we're basically going to take a strip line of data in black and white format for every millimeter or half millimeter, whatever we set, of movement down that weld. All we do is we color code the entire positive and negative scale of that raw signal, and we plot that as a certain tone on a grayscale, typically 128 grayscale, which allows us to have a display similar to shown in the bottom right here. Basically a slice put together into a single view, so we have the entire scanned area as a whole picture. This is typically represented as either a B or D scan, or we can just call it a side view. Different manufacturers will give it different names. But basically we're able to see the entire entry surface, or the lateral wave, numbered as number 1. We're able to see the entire back surface, numbered as number 4 here, or back wall, or ID surface of a pipe. And then we're able to hopefully be able to pick out distinct flaws shown here. So if this was a crack or a lack of fusion laying in a component, not only do we have positive and negative differences between the lateral wave and the back wall, but the uppermost tip and the bottommost tip of that vertical flaw will actually have inverse positive and negative values. This would allow us to precisely position cursors and other measurement tools on top of those tips and get a very accurate assessment of its height. So why TOFD? Why do we use it? There's a lot of different reasons, and it kind of depends on some of the variables. But some of the overall main benefits: it's a permanent data recording with imaging. So typically it's used with an encoder, so we have an audible result that we can store digitally for the life of the component or the life of the contract or whatever it may be. Very useful imaging of a very large volume of the material, so we're able to get a whole picture of the entire area scan, the entire weld, the entire wind tower, whatever it may be. So we're able to look at lots of information offline and revisit that information. Very large coverage area from very small footprint. Familiar with phased array, which Olympus also is in the business of. It also gives us a large coverage area, but TOFD typically can use very small probes, and because we manipulate that beam spread, we can get a very large coverage from a single set of probes and a very large amount of coverage from multiple sets of probes. Very fast and inexpensive. It's very fast because we're only using one beam. In contrast to phased array, for a typical 1/2 inch, 3/4, 1 inch weld, we might have 70 different beams to get full coverage from both sides of the weld, where in that thickness zone, TOFD might be able to do it with some very small dead zones, but pretty much 100% coverage with just one beam. So that means we can move at a magnitude 70 times faster in a typical application than a phased array. Also very inexpensive comparatively, usually very similar to conventional pulse echo transducers, composite materials, so kind of the high end of them, but you're talking hundreds of dollars typically versus maybe thousands for a phased array sensor. Reduced mechanic because we use small probe. We might not need the same ruggedness for the jig or the scanning device. Very easy to set up. Because we're only using one beam, because we only really need to set a simple display and make sure we have the adequate signals on the screen before we start. It's very easy to set up. Does not rely on amplitude. So with most ultrasonic techniques, one of the downfalls is we base everything off a reference reflector, which are perfect things, notches, side drill holes. Reality is flaws are very multifaceted, they're misshaped. So amplitude techniques are great, they work great, but there's some inherent error that goes with things like negative 3 dB, 6 dB sizing. So you never really have a beam half on and half off a flaw. Because we use time of flight, we're not subject to those amplitude sizing errors anymore. So we're using time, which is absolute. We're able to get a much better precision on our sizing typically. And really in height, the height plane and the depth plane can be quite excellent with TOFD. Also, it has a pretty indifference to the orientation of the defect. Most pulse echo techniques where we're sending sound at a given angle or multiple angles like phased array, we're still somewhat dependent on how that beam is hitting the flaw. If we hit it at 90 degrees perpendicular like we might on our reference flaw, that would be ideal, but defects can lie in many different angles and planes. So with TOFD, it doesn't really matter. If we think back early in the presentation to that diffraction concept, as long as we can hit it with enough energy, it's going to send out sound in every direction. We don't really care about how much. As long as we see it, we're able to pick up on those features like the tips and hopefully put an analysis cursor somewhere and be able to measure them. All right, flaw sizing. So just some few considerations. So if we looked at a round robin, and it's going to vary by a lot of the variables, but if you took a bunch of trained operators for really any pulse echo ultrasonic technique, and you took a group of qualified trained TOFD guys for flaw detection, you typically get these numbers on most studies that most pulse echo techniques are going to give you a sizing accuracy of about 3 to 4 millimeter. Length and height is typical, not that it can't be much better than that under the right variables. TOFDs, on the other hand, in general, will probably improve upon that, 1 or 2 with the potential to do much better for flaw sizing. And also TOFD is also used for growth. So if you actually had a flaw that you had detected with TOFD and then you recorded its size and then wanted to go back and monitor it, this might be an online thing where you don't want to take a pipe offline or a nuclear component offline. The sizing accuracy can be quite good at 0.3 to 1 millimeter typical range. Just a few different variables to consider. With TOFD, everything is about the proper selection. So typically go through and choose the proper frequency and diameter probe. You can adjust a bunch of resolutions, whether it be the scan resolution, how many slices of information you're taking, how often. Some focusing techniques where we actually focus the TOFD by the separation of the probes. Obviously some equipment and software tools. And then obviously the biggest thing in importance is who's collecting the data, who's analyzing the data. TOFD's only going to be as valuable as the person actually doing it and the training experience he has. So typically with TOFD, we use hyperbolic cursors to actually measure the length and the height of the flaw. So we can see in the bottom picture here, those are actually positioned using the different colors first and then going to the actual A scan at certain points to be able to measure the width and the height extents very accurately. This will reduce some sizing areas. The reason we use a hyperbolic cursor is basically to undo some of those effects of beam spread. basically some algorithms worked in based on the thickness of the component and some other factors, and by putting them to the natural shape of the flaw, we can actually get a better length and height measurement, which helps us make the right call. Just a few different slides of or pictures of different flaw examples. We're going to see different areas of corrosion, tips, cracks, porosities, clusters of porosities, lock of fusions, some root indications. Just some of the ways that different flaws might be examined. Often used with phased array. So on the top left there, we can actually see a multi-display of phased array and TOFD together, where we can actually look at the flaw with different ultrasonic methods collectively, which can be very helpful in assessing both the length, the height, and the other characteristics of the flaw. Some of the limitations. So the blind areas we talked about earlier, call them blind. A lot of people call them dead zones. I don't like to use this term. At the top, there will always be what could be called a dead zone. So there's a small area, typically a couple of millimeters depending on your setup and some other factors, but this is because it's not really a surface wave, so that wave needs a little bit of material to travel in. There will always be a small zone that we're not actually covering with a single TOF pair. This can be reduced by the proper selection of some of those factors, the separation of the transducers, the right frequencies, but it's always going to be there. The other one, known as a blind area, or sometimes called a dead zone, is the back wall. This is typically an area of concern because of the large amount of energy. Again, it's a very flat surface or a very large surface if it's a pipe. There's a lot of reflected and diffracted energy. This can actually be reduced to be pretty small and actually negligible. Typically when you use one pair of TOF, we're only thinking about focusing at usually 2/3 and then flooding the entire component with sound and trying to get a 2-probe full coverage type setup. We could actually do a second scan, separate those probes out further and focus it, say, 90% or somewhere near that, near the back wall. Or we could use a scanner that could hold 2 sets of probes, and we can prove up on reference reflector that basically that dead zone or blind area is pretty much reduced to 0. Some of the other limitations known to be associated with TOFD is interpretation of data and training. Because we do use different things that a typical ultrasonic inspector may not be familiar with, definitely imaging, the unrectified signal, the grayscale display, time of flight for measurement versus amplitude. It can be a little bit of a learning curve. So you want to make sure, as we'll see later, you set up with the proper training partner, the right amount of training, but it can be a little overwhelming to be able to identify flaws correctly. So it does take a little bit of experience of looking at different flaws and how to correctly analyze them, characterize them. Also the sensitivity. TOFD is very, very sensitive. If we can vibrate a flaw and pick it up, it typically will pick up even small grains or negligible flaws. So people see this as a downfall because when you look at the data, if you have a large grain material like austenitic or a casting, some other ones that have very large grains compared to carbon steel, especially, it can show a lot of different things that may not be critical or may not be a detriment or a discontinuity to the actual piece. And then one downfall of the normal type of scanning is basically index positioning. So if we were to scan a weld, straight down the weld, detect these flaws, we'd be able to measure the height, we'd be able to measure the length very accurately, but we honestly wouldn't know with that single test whether that was in the middle of the component, over here on the right on the base metal, or on the left on the base metal. We'll talk about that a little bit more, but there's ways to narrow that down or actually calculate it, but with a single pair first volume inspection, you're not going to know that positioning. All right, 2 main types of TOF scanning. So basically we define this by the direction of the scanner in relation to the beam of ultrasonic energy. So one is called perpendicular. So on the top, we're basically scanning down the weld and the beam is going across. So the scan direction and the beam are perpendicular to each other. This is by far the most common for obvious reasons. We want to do a whole length of weld very quickly. The other type is the parallel. So we can see here the encoder has been switched to the same direction as the beam, and you're actually rastering across the weld or component. Now this obviously has a limitation that any weld reinforcements in place is not going to allow this to happen. So a lot of cases we'll do a perpendicular scan, get a diagnosis, and then maybe a small amount of reinforcement may be removed to get a parallel scan. Parallel scan will give more accurate sizing capabilities, especially in the height plane, and it will also position the flaw very accurately as well, but it usually has that limitation. So if you want to get that index position with a perpendicular scan, the easiest thing to do is go back with a pulse echo probe and just get the index exact positioning that way. So by far, because of the fact that a lot of welds have reinforcement in place, and also because we want to do a very rapid scan, most TOF scanning is done in the perpendicular or non-parallel fashion. You can see a little differences there between the two. So application summary. There's a lot of applications of TOF, but by far the two biggest ones are for weld and for flaw detection, and one for corrosion and erosion. So when we look at weld inspections, we're usually doing one of two things. I'd say about 80% or better is for volumetric flaws within the weld, and then a little bit on sizing and monitoring, so as kind of a complementary technique. If we know a flaw is there, we want to watch it to see if it grows before we have to make the call to shut that down when it becomes a critical length or height. And the other one being corrosion. So on the display, you can kind of see the differences here as well. So TOF for welds, just a little bit more on the overview. It can be used as a standalone, just trying to do very quick screening or volumetric flaw detection of welds, typically using a single pair. A lot of times we use what we call the 2/3 rule. So without going too much into the complexity, but we set the spacing of the PCS of the wedges so that the center beam that the wedge is designed for is basically intersecting the thickness at 2/3 of the nominal thickness. This will give us, usually with the proper frequency and size of probe, that pretty much full volumetric coverage with the small dead zones, and allow us to do a very good inspection. Also, lots of multi-TOF inspections. So as we get thicker, that 2/3 single probe is not going to give us that full coverage. So we'll actually position multiple sensors at different spacings and different focuses in order to give us coverage of a thicker component. And then all kinds of combination, especially the codes in North America, they require the coverage of those dead zones. So we can actually get a scanner and either put phased array with TOF. We can put simple pulse echo shear wave transducers with TOF. We can use a creeping wave transducers to cover the top dead zone. But it just gives us that added coverage, and it also allows, if those transducers pick it up, to get accurate index positioning or volume positioning of the flaw as well. So typically with the zone, we're going to zone it out with different flaws and do the inspection. So for defect sizing and monitoring, typically we do this only if we know there a flaw exists. So it's used a lot in nuclear, as well as some oil and gas, some other industries. But basically we have a flaw, but it's not to critical height or length yet. TOF is very good for this, typically the parallel fashion, where if we can remove that reinforcement or we don't have reinforcement, we'll get a first sizing, and then a certain interval of time we'll keep going over and over that flaw and just seeing if that defect, typically cracks, are growing. It's pretty limited, but mainly in the power generation industry. But when we do this, we're going to basically adjust the focus for the flaw. So knowing its location, knowing its current size, and then keep the same setup and go over it at different intervals. So TOFD for corrosion and erosion. This is becoming much more popular today. It's very rapid screening. We can see here examples of different types of corrosion that happen: root erosion, preferential weld corrosion, flow accelerated corrosion. So typically a single TOFD pair is used for this, maybe more if it's thicker, but because we're looking typically at the inner surface of, say, a pipe or something like that. We usually focus near the root, 75, 90%. Does not require cap removal, so we're able to get even areas directly under the cap because of the technique of TOFD. So it can be very good without having to remove that cap compared to, say, pulse echo conventional. Typically when we do this, to get proper measurement, very precise remaining wall type measurements, we're going to do a scan at maybe 3 different index positions. So it's kind of shown there in the bottom. This is going to increase our accuracy in the actual remaining wall thickness. So we'll do one centered around the weld, and then one offset one way, and then offset the other. This can be done all collectively if the unit can handle that many channels and you have the right scanner, or it can be done in 3 separate acquisitions and the data compared that way. So some things to consider when you look at TOFD equipment and what do you need. Obviously, what techniques you're going to use, just TOFD in phased array. What channels are required? Do you need a single channel because you're only doing smaller thicknesses, or do you need multi-channels of TOFD to do multi-TOFD? Obviously, the individual equipment characteristics like signal quality, the amount of voltage, its pulse repetition frequency, things like portability and durability for the environment you work in. How long does the battery last? A lot of important features like, does the software offer unique TOFD features that make the acquisition analysis easy? And then, of course, something to do with the company. So the cost and value, the service and support, how easy is it to use? And then if you have any code requirements, things like linearity, of course, most modern equipment is going to meet this unless it's a very low-end piece of equipment. So talking about the software is really what we've tried to do, and I think other manufacturers as well, is we try to build it in a workflow-oriented fashion. So we allow you to design your component and inspection, take that, import it into the instrument, go ahead and do your acquisition, and then bring it over to an analysis program or do the analysis directly on the program. So we try to set it up as how the TOFD job goes and make it kind of a step-by-step process. So just different things in the software. There's a lot of specific TOFD tools you'll want to look for, things like the ability to linearize the top wave. Sometimes when we're scanning, if there's a slightly irregular surface, varying amounts of coupling, this lateral wave can get a little bouncy. We actually have tools where we can sample that. We can actually remove it to look at flaws that are very close to the surface, or we can just straighten it out to get a common 0 point to do our typical measurements. So TOFD probes, typically composite material, also used in shear wave. You might have some of these for your typical conventional shear wave inspections. What we want to look for in TOFD is a high quality transducer because we want to limit the ring and the cycles for resolution. So if you look at the A-scan at the bottom, we want very clean peaks. We don't want a very broad signal. So when we highly dampen the probe, it basically makes a tight signal, and that allows us to accurately use the A-scan to do very precise measurements. If we had a very broad signal, our accuracy and thickness, our length and height measurement is going to be reduced. Just some things to consider. Smaller diameter is going to give us a better beam spread, so more volumetric coverage. So we typically use very small elements, 3 millimeter, 6 millimeter crystals inside the probe to give us that better beam spread. Typical range of frequencies are about 0.5 meg to 15 megahertz, and they can go lower and higher, but typical industrial applications are right in there. It can depend on the material, the thickness, the resolution needed. Anybody that does TOFD on a regular basis is wanting to have a whole collection of different probes, frequencies, sizes, because the individual parameters of the probe is going to make a big difference in the resolution you make with TOFD. Just a real quick look at the wedges. These are typically matched to the probe for proper sound propagation. Typical standard wedges come in Rexolite or plexiglass, stainless, some other types of materials. We can see some different examples here. Typically fed with irrigation ports so that we can have water flowing through them to act as our couplant, very consistent couplant. Forks to mount on the scanner. Some have adjustment pins so we can set the height and leave a small amount of couplant underneath. Other ones, like the stainless ones pictured here, can ride directly on the component without the use of a pin. Not have to worry about too much excessive wear like the plastic would wear over time. Obviously, for curved components, we're going to match that curvature as closely as possible to the component that we're inspecting. And then we have special application type things. The bottom right is actually a wedge made for HDPE pipe. This actually has a water interface and a seal that will seal. And the reason we do this is because the natural velocity of HDPE and other plastics is too close to Rexolite, so it can cause issues in getting the proper beam propagation. So by using water, we're able to do that very easily and conveniently. And the most common angles, typically where 45, 60, and 70 are the cut angles, but obviously we have a spread of a big wide coverage of a single beam, and we have all different types of angles that are available from different providers. So TOFD scanners and accessories, all different types. Basically we mate this to the need. Main features, is it semi-automated, meaning it's operator driven, or is it motor driven or fully automated? You really base this then about, does it have the features you need, magnetic wheels or a chain base, and how many probes and wedges of what type can it handle. Other TOFD techniques, there's a chance to do multiple skip where we're actually sending the sound in and it's bouncing off the various interfaces multiple times. This is actually done when there's a limitation in access or there's a component in the way. It can also be used just to improve the near-surface resolution. Not so popular, but it does happen. Same with same-sided access. So we can actually position the TOFD probes on one side of the component and try to get a diffracted signal back. Again, very difficult to plan out compared to double-sided access, but it is done in some special applications. There are instances where we actually use the shear wave component as our main component, so we have to have specialized wedges. We do this for certain sizing characteristics and also in a lot of the multi-skip because shear waves give us a better dependent skip off parallel surfaces. And in some cases we'll do timed with no encoder, but this is pretty uncommon. Sometimes with two-man teams it's possible if a guy actually had some markings, he could do some really quick screening tools and get some semi-practical length sizing, but it's not going to be as accurate as using an encoder with a scanner. So TOFD on thick materials, we're looking at a few applications here, and we're running low on time. I have a little short cut in my display coming up, so I'm taking a little extra pauses, but we'll get through this real quick. TOFD on thick materials. Here's an example that I had this year, so a 400 millimeter thick pressure vessel using different zones of TOFD, and we actually combined it with phased array. You can see here's our calibration block. Basically looks like a big coffee table. Very impressive calibration block, side drill holes all the way through at different zones so we could prove our accuracy, our resolution, and our detection capabilities. So here's a schematic of how we set it up. So we had actually 5 pairs of TOFD in order to cover all at different focus zones. Here's the display. So we're able to detect all these defects quite well, actually. So you can see the different zones, different defects coming up in the TOFD. Obviously a little hard to see in the display here, but basically split it into zones, each pair responsible for a certain zone, which is typically what we do, so that we don't try to use a TOFD single pair for too big of a zone. We're going to lose resolution and sizing capability. So by splitting it up like this, It's really the way to go when we talk about thick components. So in the end, we're able to look at this in a software program along with the phased array and have multiple hits on the different flaw types and a very high probability of detection. So in this case, even a 3 millimeter notch at the bottom was detected with the TOFD. And that's really an area that we focused on the phased array as well, because it was the one indication way down at 400 millimeters that had a little bit lower resolution on the TOFD display. So we're able to get full volumetric coverage except for the very top, which we covered with a magnetic particle inspection was done anyway to cover that zone with a very high signal-to-noise ratio. Kind of the opposite, TOFD on thin wall piping. This can be a difficult application for ultrasound in general. This example is 4.6 millimeter thick, 45 millimeter diameter piping. We have specialized wedges due to the popularity of our Cobra system for weld inspection. We decided to add TOFD for things like corrosion erosion evaluation, as well as just to have a complementary TOFD inspection for flaw detection. One consideration as we get thinner with all ultrasonic materials is at some point it becomes maybe a go, no-go inspection. So the ability to accurately size things due to the relationship of the thickness and the size of the flaws versus the beam might not be possible or might not be as accurate. So we can see a variety of defects there shown, cracks, lack of fusion in a very thin material, but we may not be able to size those. We might just say, yes, there's a crack there. We've also had a lot of success with this application with some varying materials like copper nickel. Some emerging trends and where TOFD is going. So special materials, the HDPE market, plastic pipe, a lot of pipelines going up, very easy to use TOFD to get a very good volumetric screening. Copper nickel, some research into cladding and austenitics. It's being used more and more, but these usually have varying grain and large grain structures, so TOFD is usually not the first one to be selected. But used in some specialized application in specialized ways, it's increasing. A lot of development in signal processing to be able to improve upon the sizing capabilities of TOFD, even more so than it can already provide. Things like SAFT or synthetic aperture focusing technique, shown in the middle bottom there, where we can actually post-process the imaging, remove certain components, like the beam spread component, and be able to accurately measure even more so. Phased array generated TOFD. So here on the right-hand side all the way down, we have phased array transducers that were designed to do actually all three different setups of TOFD that we would use in corrosion and erosion all at once, and be able to display that in a very familiar format, 3 TOFD displays, and just give us a good ability to do it very accurately, positioning the phased array transducers. So just really briefly on code standards, recommended practice, and the like, because it varies globally so much that it's hard to talk to specifics. One of the big ones for North America especially is ASME Section 5, Article 4. They have written a mandatory appendix, and this is typically what's followed. It gives recommendations on calibration and blocks, the performance demonstrations that are needed to be done, how to set up, probe and angle recommendations, as well as some variables. A lot of different special codes cases out there. A lot TOFD can be used for all the radiography replacement codes, as long as all the considerations are taken care of. Many different interpretation manuals, recommended practices, several ENBS European references. API recognizes TOFD for a lot of applications. All the North American codes really require at least some designation, whether it's by manual shear wave or using encoded shear wave or phased array to compensate for those dead zones that we spoke of. TOFD training, I invite you to go to our website, which the URL is there. We have a large academy of training members that offer TOFD training. They can also answer more questions about how to implement TOFD into your company. ASNT, PCN, a lot of other certifying bodies have entire schemes for TOFD levels. A lot of times you'll start with a typical shear wave guy that's using Level 2 maybe manual weld inspection, or he has some automated inspection before they get into TOFD. Very typical is a 1 to 2 week classroom type recommended training on top of a certain amount of on-the-job training hours. I'd say the key critical point is data interpretation. You want to hook yourself up with a trainer that spends an adequate amount of time on the data interpretation, because setting up TOFD is relatively easy. It's in the proper interpretation and characterization of flaws that can be a little more difficult to learn. And a lot of these will have written and practical examinations, which I recommend for any ultrasonic technique in order to ensure that the training was well received. So that really brings us very quickly to our very broad overview. I want to thank everybody for attending. It looks like we're getting close to our time, but I think we probably have time for 1 or 2 questions, so I'll go ahead and turn it back over to Sam.
Thank you very much. So yeah, it's time for the question and answer session. We've got plenty of questions in, so I'll dive straight into those so we can answer as many as possible. The first one I'm going to go to is, how can we choose the right angled probe for use in TOFD? Okay,
that's a very good question. Normally with TOFD, what we do is, well, 2 ways. A lot of those guides I talked about from the different ASME API, a lot of them will have actually for those types recommended tables for different thicknesses. So you base it on thickness. It will give you the size of probe, the frequency, as well as the wedge angle to use. This is a first guide to know which equipment you may need for your range of applications. But second, you use a setup software. So either on the instrument or in the pre-setup software that allows you to actually draw your weld or component in and place the transducers and adjust the variables. You will look at the proper setting of the spacing of the transducers, which wedge, and it will actually give you a theoretical display of how much coverage you're getting and all the other variables. So this would help you actually show that you're getting coverage as well as the proper resolution, etc. But on top of that, well, as with all ultrasonic techniques, the practical checking on a reference standard is often best. ASME specifically in the mandatory appendix will make you prove sensitivity and resolution of flaws on a recommended demonstration block. So there's kind of 3 ways that you kind of get to that. So you have a basic guide, you have design software on board or offline that allows you to actually design your application and display it. And then you have, in a lot of cases, a reference sample made that has the same variables as your tests, and all these, or any version of them, is going to lead you to the right selection of probes and wedges. Do you have another question, Sam?
Yeah, thank you. So the next question I've got is TOFD enough for weld defect characterization, or additionally should we inspect PA or manual for defect characterization?
Another very good question. So typically it's good enough for defect characterization. I say that with a little bit. Adding phased array is great. I think the complement of the 2 is one of probably the best ultrasonic techniques we have today. That obviously comes with an added cost, an added setup time, investment in equipment and training. By far, the combination of the 2 is going to give you the most powerful tool. TOFD by itself can be a perfectly good characterization tool for most flaws. But with that, it does require that adequate training. The more experience that person has of looking at flaws, or the mentoring of somebody in the program that has the on-the-job experience, it really takes looking at the defects and doing it. So starting out can be a little more difficult because of that fact. You want to make sure you get the proper training, heavy on the analysis side. But used with a qualified guy that has that experience, it's a very good standalone. You could also go back to just simple pulse echo. So use a TOFD as a very fast screening tool with recorded data and imaging. And then maybe depending on your defect rate, just going back manually, something that you're familiar with, and using the pulse echo shear wave or something like that is a very valid technique I see a lot of customers do as well.
Okay, thank you very much. We're pretty much at the end, but we'll squeeze in one more question, just something for you to clear up, which would be, what are the biggest limitations or challenges to applying TOFD?
Okay, another good question. So it depends on your business, your use of TOFD. We've mentioned a few already. So the biggest limitations, I would say, from an acoustic standpoint, is how do we account for dead zones? The near surface dead zone is always going to be there. If it's used just as a screening tool, that's not too big of a deal. But we need to account, if we want to call it 100% volumetric inspection, that would have to be covered by another technique that would cover that small dead zone of the TOFD, whether that's pulse echo, whether that's phased array, whether that's mag particle eddy current, something else that can detect down a millimeter if that happens to be the dead zone. To do that, so there's that one consideration. Another one is, as we've alluded to multiple times, is the characterization. The flaw and characterization analysis is difficult, so we overcome that by, again, the proper training, the proper on-the-job, or the complement of other ND techniques to validate that our calls with TOFD, especially as we first implement the technique, are correct and valid. I think over time you gain that experience where you could go back to using just TOFD, but in the beginning it might be one of the biggest challenges is understanding everything we're looking at. There's also the fact that in some materials, and even in carbon steel sometimes, very small porosities, large grains, they show up in the display, so you can get actually a lot of signals and have to be able to quickly go through that and determine what is non-relevant and what isn't. In most carbon steel applications, this is not a big deal, unless your process has a ton of small porosities that might be sub-millimeter, sub-half millimeter, but TOFD may in fact show them as individual little pores, and you have to make that distinction and be able to quickly discard them if they're not relevant to your process. So just a few of the challenges, but I think all of it comes down to is just thinking about the proper way to implement and doing it. I'd say one more big one is, and kind of the reason TOFD kind of got a bad name for a few years, was it's almost deceptively easy to set up. It doesn't take a lot of parameters. We basically can set it up very easily based on the thickness of the part. All we do is set up the instrument to display the proper signals, and away we go. So that can give a little bit of overconfidence in the technique. Those little variables like which frequency, which wedge, angle, the size of the probe, these are important considerations when you actually detect the flaw. So am I able to measure to what accuracy? Am I actually covering the area I think I am? The back end of it is one of the challenges. You want to make sure that you have the right tools, you have a good instrument and a selection of probes and wedges, and prove it up on a block and then the theoretical design software properly.
Okay, thank you very much. So that pretty much brings us to the end of the Q&A session and the end of the webinar. Sorry if we didn't get around to answering your question, but these will be passed along to Nicholas, and you're also able to leave additional sort of feedback or questions in by the survey widget, which will pop up as soon as this webinar ends. That will be replaced by the survey widget for you to fill out. This just leaves me to thank Nicholas for his great presentation and Olympus for sponsoring this session. Again, to the attendees, you'll receive an email shortly telling you how you can access this on-demand version. That will be in about 2 hours, or you can find this through our website, which is www.business-review-webinars.com. There'll also be a PDF version of the slides attached. I know a few people have asked about that. So if you log into the on-demand version, click on the resource list, you'll find a PDF there to view or download. We look forward to sharing further webinars with you, so please keep an eye out on the website I just mentioned. Follow us on Twitter, which is @BRWebinars for daily updates, and join our LinkedIn group, Business Review Webinars. Apart from that, thank you once again, and I hope you all have a nice day.